Hello everyone, here we have another Physics 30 example. This is lesson 4, the electromagnetic radiation unit, and this is lesson 4, which is refraction. So here we get into some Snell's law stuff. We have a situation where a laser is being shone through water. It reflects off of a different object and returns in a total time of 183 microseconds. We need to determine the distance to the object. This is of course how radar and sonar and all of that kind of stuff works. So what we're going to do, let's do a little sketch here. We're going to say that the light starts from here. It's going to travel, obviously in a straight line, not like my line, all the way to an object. Let's call it a mirror. And then it's going to come all the way back. And if you knew the time that took, and you knew the speed with which it was traveling, you could then work out the distance. We're trying to find out how far it is away. Now, all we have is the refractive index of water. So we need to use our Snell's law a little bit here. Let's go ahead and put in N1 over N2. And so let's go ahead and assume that N, actually let's rephrase that. Rather than N1, we'll call it N, N of air. Okay, the refractive index of air, which we know to be approximately 1, good enough, same as a vacuum, over the refractive index of water is going to be equal to the speed, and this is where it's an inverse rule, the speed of light in water over the speed of light in air. Now, this is the cool part, because of course we know some of these values. We know the speed of light in air, and we know the refractive index in air. So let's just restate this in terms that are going to be familiar to us. Let's restate it as N in air, so 1, because that's what it is, divided by, well, the refractive index in water is given, so I'm going to put that in as 1.33, is equal to the speed in water. I'm going to need to know that in order to solve, in order to solve this situation over here, over the speed of light. Okay, so let's go ahead and solve it for the speed in water. So it's going to be the speed of light divided by, actually let's put it in as the value, so 3.0 times 10 to the 8 meters per second divided by 1.33. And that gives us the speed to be 2.5556, and we're going to keep all of these significant digits in our calculator, times 10 to the 8 meters per second. Okay, now we can come over here, over on this side, and start figuring out what's going on. We know the speed, so let's go ahead and put this in right away. So 2.5556 times 10 to the 8 meters per second is going to be equal to the total distance, so all the way there and all the way back. Okay, and that's important because we are told that it reflects off the distant objects and returns in a total time. So the total time is there and back. So I need to state that that's 2d. It's 2 times the distance. So that's going to be 2 times the distance, let's put it like that, divided by the time. Well, the time is given to us, 183 times 10 to the, well, micro is -6 seconds. So I'm nearly there. I'm going to solve this. I'm going to say that, what am I going to say? I'm going to say 2.5556 times 10 to the 8 meters per second multiplied by, hopefully this is going to make, it's going to fit in, multiplied by 183 times 10 to the -6 seconds divided by 2. That's going to equal the distance one way. In other words, the distance to the object. And if you plug that into your calculator, you're going to get 2.0639, some other some other digits, times 10 to the 4 meters. In other words, 20, nope, back up, 21 kilometers. Okay, just checking my significant digits. Oh, actually, I should have checked that first. Let's see, I've got 3 here and 3 here. So yeah, I should have put that to 3 significant digits. So I would actually say 2.06. Oops, made another mistake. I'm going to say 20.6 kilometers. There we go. That's better. Okay, so for example 2 in this section, we are just qualitatively predicting the directions of the refractive ray out of the glass. We're assuming it makes it out the other side. So we're going from air to glass, and it's important to just think this through qualitatively. So if you're going from air to glass, the refractive index is going to go up. And if the refractive index goes up, then the speed is going to slow down, because we have, remember from Snell's law, let's call this 1 and this 2. N1 over N2 is equal to V2 over V1. And that says, let's think this through, if the refractive index in glass is bigger, if this goes up, that means this goes down. So the speed within the medium is going to go down. In other words, the speed of light in glass is going to be slower than it would be in air. Okay, so let's think about what that does to the wave, and again, just qualitatively. So let me just get rid of this stuff here for a second, and we're going to think about this, and I like to use the analogy of a 4x4. So a car that has 4-wheel drive, here it is. We're viewing it from the top. It's got 4 wheels, there it is. And it's heading towards the medium where it slows down. So we'll use the analogy in class of a 4x4 going from concrete, so let's say, or tarmac or whatever, a road, to mud. Okay, so you can travel faster on a road than you can in mud, sticky mud. So if we imagine, as this car is coming up, because it's coming at an angle, the wheel that hits the mud first is going to slow down first. So take a look. This is the wheel that's going to hit the mud first. The right side of the car is going to hit the wheel, the right front wheel of the car is going to hit the mud first. It's going to slow down. So if the right side of the car slows down first, it's going to turn to the right. So our light ray is going to go this way. It's going to slow down first. Okay. Now it's in the mud, and the car, let's redraw the car over here. Here it is, car in mud, 4 wheels, 1, 2, 3, 4. It's still going at an angle. And so which wheel is going to hit the fast road again? Because of course it's going to come out the other side. You're going to have road conditions over here. So which wheel is going to hit the road first? Well, hopefully you can see it's the same front right wheel. Well, if the front right wheel speeds up first, the right side of the car is going to speed up, and that means it's going to turn to, let's carry this on, it's going to turn to the left slightly. And there you have it. It's going to go through, and this is a familiar pattern, I'm sure. What's interesting about this is we have this bending here and the bending here. This ray here and this ray here will be parallel. Okay, and so we can start making some statements about the angles, and we would go through and do a similar thing that we would in our mirrors. We'd put our normal lines in. We would start identifying the angles relative to those normal lines, but in this case we're just asked to do it qualitatively. Okay, let's do B. Okay, so B, and it comes. I'm going to draw my little truck again, my 4x4. Here it is. There's my 4x4, and there's my wheels. Which wheel is going to hit the mud first? Can you see? Yep, it's this front right wheel again. So the front right wheel is going to slow down first, which means it's going to turn to the right. So I'm going to get some kind of turn. Now this is interesting, I don't know the values here. So it's going to either go to the right this way, but it might even go really to the right. We don't know that from this scenario. Maybe it's going to go all this way. So we've kind of got two different situations here. Both are going to go to the right. Okay, let's just think about what that means as the light leaves the glass. So I'm going to do two little trucks, one here and one here with the wheels. Okay, which wheel is going to hit the road first? Well, which wheel is going to hit the road first? Hopefully you can see it's going to be, let's take a look, this one, isn't it? It's the left side of the car. So the left side of the car is going to speed up, which means it's going to once again turn to the right. So this ray is going to continue getting bent that way. Okay. Same for the other truck, the other possible scenario. This guy over here, oh actually no, it's the other way around. This one down the bottom, the right front wheel is going to speed up first. So in the bottom example, it's going to go this way. The right side hits the road first and therefore speeds up first. So qualitatively, I can say there's two possible options for the prism, but those are the ways we should be thinking about this. Of course, light doesn't really behave like a 4x4, and we can go through this in class. There's lots of really cool stuff we can talk about with light as it goes through a different medium. Why does it slow down? Should we think about it as a wave? Should we think about it as a photon, a particle, etc., etc.? But for now, that's going to be good enough that we'll get some solutions from our problems with this way of thinking.